all we need to know are the values of A, H, and K. And I know it seems like it's been months since before break, but you guys were very good at that. You were always able to tell me right away what the values of A, H, and K were, right? So let's do just a quick, literally like 20-second review here. So we know that whenever we want to graph a parent function, or graph a transformation of a parent function, we're always doing something like this. We're going to compare the parent function to the transformed function. Okay, so if our parent function in this case, we're going to look at this. I won't even use x squareds for a second. If the parent graph, we'll call that p of x. That's our parent graph. And we're going to do, we want to create some transformation of that. Well, we want to know what are the values of A, which is the number that's the coefficient that's outside of the whole thing. We want to know what's, tell you what, we will do it this way. We'll just call p of x squared. We want to know what's the number that's being subtracted from x inside the function, which is h. And we want to know what's the value of the constant that's being added outside the function, which is k. And think what the jobs of those three parameters were. H was the horizontal translation, right? K was the vertical translation, and A was the vertical dilation factor. So you guys tell me real quick, what are the values for this function then, or for this example, what are the values of A and H and K? What's A? -3, isn't it? Good, okay. -3, what's the value of K? That's an easy one. -2, good. That's the one that's outside. And then the tricky one, what's the value of H? 3, good. It's +3, because it's the number that's being subtracted from X. Okay, well then what's that do? What do the values of H and K do? That's just translating this thing, right? So how far are we, in what direction and how far are we translating it horizontally? What do you think? Whose job is that, A, H, or K, to do horizontal translations? H, okay. So if H is 3, if H is +3, then that means we're going which direction? Right, there you go. So this means we're going right by 3, okay? K is -2. What's that telling us? Down 2. What the heck? How did that happen? This board's got some kind of funky little, I think if I put my hand real close to it, does it do that? Yeah, that's weird. I gotta get used to a few. I'll take it though, I like it. So we're going down by 2, over by 3. Now, to get us ready for the next section, which is just about vertex form, let's kind of just think about how we might be able to graph this thing then. So the vertex is the point that starts off at the origin for an x squared graph, doesn't it? Everybody agree? Right? Well, the vertex, instead of being at 0, 0, if I slide my parent graph right by 3 and down by 2, doesn't that just mean that my vertex is going to end up being over 3 and down 2? Right? So here's going to be the location of the vertex right there. Okay? Okay, now here's the tricky part. The vertical dilation factor is -3. Okay, think what that does. It's going to vertically stretch or compress and possibly reflect the function, flip it vertically, by multiplying the normal parent function heights by whatever that coefficient is, in this case, -3. So what's helpful to do here, at least initially, at some point you probably won't have to do this anymore, but what's helpful to do initially is to maybe, wherever the location of our vertex is, let's just make a light graph of the parent graph, what that would do. So for our parent graph, x squared, what's the rule? From our vertex, if I go right by 1, how far up would I go? 1, exactly. I'm going to go over 1, and I'm going to go up 1 squared, which is 1. I'm going to go over 2 and up how far? 4, yeah, over 2 and up 2 squared, which is 4. And so look what's happening. I'm getting a shape like that, right? And it's symmetrical, isn't it? If I go back 1, I go up 1 square, or up -1 squared. If I go left 2, I'm going to go up by -2 squared, which is 4. So it's going to have the same shape on that side, right? Okay, but I'm multiplying by a dilation factor of -3. So all I have to do then is I'm going to multiply my normal parent heights by the dilation factor. So for example, instead of going over 1 and up 1, from the vertex, I'm going to go right 1 and up 1 times -3, right? So I'm going over 1 and up -3, meaning down 3. Over 1, down 3. Over 2, and instead of going up 4, I'm going to go over 2 and up 4 times -3. I'm actually going to go down 12, right? Which, oops, hang on, give me 1 sec here. Hey, Mr. Morioka. What's up? Yeah, are you good for... Okay. Right, and so then what's that do? It ends up, because we've got a negative dilation factor, it's opening down instead of up, so it got reflected, we could say, right? And it's being stretched. So the shape would end up being something like that. Everybody get it? Okay? The key there is, and I know it's been a long time, the key is always to write down what those values are first. And once you write those values down, it's easy to graph. Okay? All right. Now, how does this one, I just want to see how this one works in the computer. So, where'd it go? Right there. Oh, there's the preview right there. Okay, so what do we need to do then? They want us to graph this thing. Boy, that's tiny. We would just use this parabola tool. Okay, right? And then we need to pick 2 points. So we're going to pick the vertex would be notice you can see the vertices, the coordinates of the points I'm picking. So we've got one at, what did we say, over 3 and down 2. So over 3, down 2, there's a point. And then we need one other point on the parabola. So we go over 1 and up 1 times -3. So we go over 1 and down 3. There's my other point. I got it. Okay, make sense? Okay, give me 1 to 5. How are we doing? Okay? Excellent. All right, another one. 8, okay. 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 So there's the picture, right? They're giving us the graph, and now they're wanting us to answer these questions. Okay, so first of all, which one of those is it? Is it absolute value of x or square root of x? Okay, it is. How do you know? What's the clue that, how do you know that's an absolute value graph?
It's like parallel, it's with them.
Okay, well, okay. What about the, I mean, there's something you could be able to tell me right away about the shape that just says, oh, it's absolute value. Okay, how do we usually describe an absolute value graph? What's the shape of an absolute value graph? It's a V, yeah. Isn't that a V? Right? Now it's upside down, right? But remember, that's the job of transformations, is to make it look weird. But you can see that that's a graph that is a variation of a plain old V, isn't it? Because of the shape, because it has a vertex and it's got a V shape, even though it's upside down. We recognize it right away as absolute value. Okay, give me 1 to 5 on that. Are we good with that? Okay. All right, so first step, this is just a pull down menu, but what it's giving us the option of choosing is absolute value of x. Okay. Well, it's translated how many units to the left? 2, it looks like, right? Okay. 2 units to the left. Okay, I'm going to do this. Let me color code this. And it looks like it's reflected across what? Okay, the x-axis, right? It's been reflected vertically. Everybody agree? Okay, so and it's translated how many units up? 3, okay? So now I want to be able to turn those into values of our parameters. What's this telling us right here? The green 2 is being translated 2 units to the left. Which parameter is that assigning a value to? H. And what's the value of H, everybody? It's going 2 to the left. Okay, well, the value of H is -2, but here's the thing. H is the number that's being subtracted from x inside the function, right? What's always useful to do here is, let's write we've got our parent graph as absolute value of x, right? So we'll call this, what are we going to call this? I don't know, we'll call this m of x or something crazy. Where do the a and the h and the k go? Where's the a go? In front, okay? So the a is out front. Where does the h go? Okay, so it's inside, right? And where does k go? Outside. Okay, good. So that's being added out there. So now, again, what's the value of h? What's the number that's being subtracted from x here? Thumbs up for +2, thumbs down for -2. What is it? Everybody vote. It is thumbs down. It's -2.
Don't try to trick me.
How come it's -2? Because it got shifted left by 2, right? An easy way to think about this, I know this, once you've done a few of these problems, I mean, maybe you got a few more to do. I mean, I think you guys, a lot of people have a lot more to do in this assignment, so maybe you haven't gotten a ton of practice on it. But once you've done a few of them, it's no big deal. But think of H as how far H always assigns how far it's going to the right. Well, it's going to the right by -2. So that means it's going left too. Everybody get that? That's an easy way to think about it. If it's going 2 to the left, then that's -2 to the right. So h is -2, right? What's the value of k? +3, isn't it? Because it's going up by 3. That's the job of k, is to tell us how far it's being translated up. Well, the answer is 3. It's going up 3. And what's the value of a here? Okay. It's -1, isn't it? Right? Because instead of going over 1 and up 1, oh my gosh, I got to get out of that habit. Instead of going over 1 and up 1, I'm going over 1 and up 1 times -1, right? Everybody see that? So a is -1. That's the reflected part, isn't it? Okay, so maybe I should do this. Let's make that purple. So it didn't really ask you to do this, but what I would rather the problem had asked you is how write it. They gave you the graph. How would you write that function?
It does ask us to do that.
Oh, it does ask for that. That's the next part.
It says give the equation.
Is give the equation. Perfect. Okay. So now we got to give the equation. Okay. So we've got all that information. So what's this thing look like then? Okay. So we called it m of x. Could call it anything. Doesn't matter. So what's it going to be? Corey, start us off. Okay, -1. And because it's whenever -1 gets multiplied by something, we just call it a negative, right? That's what's outside. So now I'm starting my absolute value bars. What's going inside the absolute value bars? X. What do you think? Ashton, what goes inside there? +2. Good. Okay, because it went left by 2. And then finally, what's going outside here? +3. There you go. So there's our answer to the second part. Okay, give me 1 to 5 on that. How we doing? Okay. Oh, that looks good. It's climbing. Okay, any other ones you want to go through? 3, okay. And I'd go ahead and, like, if people want to just start working now and just casually glancing up, I'm fine with that. I'll continue to do problems, to go through them if you want me to, but the rest of you guys, if you want to, if you feel like you're good, just keep working. Okay, number 3. Okay. Yeah, okay, this is a good one. I would highly recommend everybody watch this one. I know I just released you, and you can, that's fine, but. Okay, let me. Okay, so our parent graph this time is x squared. What are the values of a, h, and k? And I'm going to type them in here just because I'm writing so bad with this new pen. What are the values of a, h, and k? What's a? 1/5. Everybody agree? Okay, good. That's the number that's outside. So a equals 1/5. Okay. How about what's the value of h? What do you think? Allie, what's the value of H? 5 is correct. Good. And what's the value of K? Miss Cedars, what's the value of K? 0. Good. Okay, so that's all we need. We should be able to graph this thing. So where is the vertex going to go then? Instead of being at 0, 0, we say it again? 5, 0. Good. Okay, so we know the vertex is at 5, 0. Okay, now we got to get the shape graphed, which is a little strange. But let's at least lock that vertex down. Okay, so the vertex is over here at 5, 0. Okay, now the dilation factor is 1/5. So we're going to be multiplying our normal heights by 1/5, right? We got to see if we can pick a convenient one. Normally we would go over by 1 and up by 1, right? So now instead of going over 1 and up 1, we're going to go over 1 and up how far? Everybody? We're going to multiply the regular height by the dilation factor. So my normal height of the function, meaning how tall is it from the vertex? Over 1 and up 1. But I'm going to have to multiply that height by 1/5. So I'm over 1 and up how far? 1 times 1/5. What is that? 1/5. That's not very convenient, is it? Right? So over 1 and up 1/5 puts me like where? Right down there somewhere? That's not very convenient. I go over 2 and up 4. Well, 4 times 1/5 is what? 4/5. Again, not very convenient, right? Over 3 and up 9. 9 times 1/5 is 9/5. So what is that? 1 4/5? Not very convenient. What did I say it was? 9/5, so it's up here. Over 4 and up 4 squared, 16/5. Again, very inconvenient. That's 3 1/5. So up 3 1/5. But finally, we get to something that's good. If I go over by 5, I would normally go up by how far? On an x squared graph? 25. 25 times 1/5 is 5. Bingo. Right? That's a good one to use, isn't it? Right? That's a height that's compatible with the fraction 1/5. So over 5 and up 5. And now we get a pretty good idea what this thing looks like. All right, it's going to look like that. Okay, good. When we want to do this one in Math Excel, I mean, what's the obvious point? Which of those 5 points do we want to use in Math Excel? We want to use that one, right? Because the other ones aren't going to work. Because in Math Excel, the points stick to the integers, right? So we have to use a convenient one where the coordinates of the point lie on the corners of the graph. You know, they're integer values. Okay, give me 1 to 5 on that. Okay, you get the trick there, though, right? The trick is we got to pick the height that we can multiply conveniently by 1/5. Okay, other ones. Anything else? Yes, ma'am.
3 and 9.
Sure. Oh, okay, square root. Yeah. Okay, I'll tell you what, maybe we'll just type through this one. Okay, yeah. Let's try this. Try to make this as readable as possible. So here's our graph, right? First thing it wants to know is our square root graph which normally would start at 0, 0. That would be the terminal point, right, where the whole graph starts. That's the one we'd use to track the translations. What's the answer to the first part? What's the horizontal translation here? 4 to the left, okay? So here, we'll pop that thing up again in a second. So we're going 4 units to the left. Okay. How many, I guess it wants stretching next. Is that what it's asking for? Okay, stretching. All right, so let's pop this thing up here. So is there any, oh, okay. You know what? I'm gonna, I see what they're doing. Oh, we're okay. We're okay. So what is the stretch on this thing? Nothing. Everybody agree? We're still going over 1, and the height is only increasing by 1. It's going in the wrong direction, right? But it hasn't been stretched at all. It's still the same shape as it was before. It's just been reflected, right? We'd go over 1 and up the square root of 1. We'd go over 4 and up the square root of 4, which would be 2. Well, we're going down 2 instead of up 2, but it hasn't been stretched or compressed. Everybody get that? So second answer would be no stretching or shrinking. Okay? Now, what kind of reflection was there? X-axis. Okay? Right? Okay, what about translation up or down? Say it again. Went up 2. Okay? Up 2, so there's our up 2. Okay, and then the last part, I don't know if we'll get through this whole thing today, is type an equation. Okay, well, that'd be a good one. I tell you what, we'll lead with that one tomorrow, and then I'm going to move into some new stuff. Did that help going through those?
Yeah.
Okay, good.